Okay, here we go. We're doing limits, day 4, continuity, and off we go. All right, let's pretend this is a road. Where would we have difficulty driving on it? So we'd have quite a bit of difficulty, right? We would not make it wherever we were going. Let's say we're starting going this way. We'd be fine driving, and all of a sudden, whoa, the road stops. There's a hole. The road doesn't, a huge drop down here. So we'd have some difficulties at 6, right? Let's just say for some reason we got back on the road. And we keep going, and then all of a sudden, no, there's a hole in the road. Okay, not too bad, but we would have difficulty, going over the hole. Plus, what is that dot up there? Is there a boulder coming down on us? So you have difficulty at -4. Let's say we got past that difficulty and we keep going. We have another difficulty here at 0. And as we keep going, we're going. Oh no, looks like we're going down to we're not stopping. So it looks like at 4, as we're approaching 4, we're going to have difficulty. So we're focusing on the difficulties of this graph because we want to talk about the word continuity and what it means, right? We talked about, remember when we did polynomial graphs, and we talked about them being smooth and continuous. So everything we've worked with so far, quadratics and well, I shouldn't say so far because rationals are not smooth and continuous, right? But quadratics and linears and cubics, those are all smooth and continuous. Polynomials are all smooth and continuous. Rationals, not so much. And then this crazy piecewise function, not so much. So we know what the word continuous means. It means like we have a curve, or whatever we have, it's like sine and cosine, they're continuous, right? It's just there's no holes, there's no gaps, there's no falling off the cliff, right? And so because we're doing calculus, there's an official way to talk about continuity. And the first thing is that f of c has to be defined. So what does that mean, f of c has to be defined? Well, what that means is this. C is any x. Let's just go ahead and pick a c. Let's go ahead and pick, let's pick 3 for our c, all right? And so we're like, all right, f of 3, is that defined? Well, let's see. What's the value of the function when x is equal to 3? It looks like it's equal to 5, right? This is 5 right here. So we're like, yep, that equals 5. We're good, okay? And then the limit of this function that we're looking at as x is approaching c has to exist, all right? So our c is 3. So let's see, we're coming in from let's erase real quick what I just did. We're still looking at 3. So we're coming in from the left, we're approaching 3 from the left, we're approaching 3 from the right, and we're approaching the same thing, right? We're getting to 5. And so we have continuity when these two numbers are the same. And this is the last part. So we have to have f of c has to be defined. We actually have to have a limit that exists. And the two things have to equal each other. So since 5 equals 5, we would say we have continuity. Now, not continuity over this whole thing. And that's the crazy thing, all right? We're talking about continuity just at a point, which is a crazy idea because when we think of continuity, we think of the whole graph, the whole function. But we would say we have continuity at 3, right? If we looked at another one like -4, we would not have continuity at -4, right? Because the value of f of -4, well, I know it looks weird, but if we're a little guy standing on the x-axis at -4 and we look up, we're going to look through the hole and we're going to say, oh, there's the value right there at 3. That would be 3. But if we were to talk about the limit, so we're going to do this again. If we did the limit of this function as x is approaching -4, we'd be like, well, we have a limit, right? Approaching this way, approaching that way. We are definitely approaching 2. So that has a value at -4. It has a limit, but these two aren't the same. And that's why it's not continuous at that point. All right, so we're really weird to think of continuity at a point, but that's how we speak about it. All right, so what is this going to look like when we do our delta math? It's going to look like this. Ooh, lots of boxes. And so what I did is I pulled up this problem on delta math so we could see how to do it there. So let's see if I can get to, there it is. All right, so same problem. So we can see at -1 that we do have an issue here, right? So let's go ahead and go through. Oh gosh, am I going to be able to write on it? I'm not sure. All right, so the first part says, since the limit of f of x, as x is approaching -1 from the right, or no, from the left, that's hard to read. So let's see, we're approaching -1 from the left, and that's going to be 3, right? So we'll put in a 3. Okay, and then we want to do the same thing at -1, but coming from the right. So here's my -1. I'm going to be coming from the right, and I'm also approaching 3. So that's good news. So we know that there is a value for the limit. So that means that the limit exists, right? I guess we had an option to say does not exist, but we know it exists, and it's equal to 3, right? Because left side, right side, both 3. Furthermore, it can be seen that there's a value for the function when x is equal to -1. So let's see. So f of -1, oh, let's see if there's a value. So f of -1 means, hey, when x is equal to -1, what's the y value? We got a big hole here. That means there's no value when x is equal to -1 for our function. So we're going to say equals, oh, why does it say, there's not a little drop down there. That's so, f of -1 is undefined. Does it tell us, oh, so sorry. Guess what? We get to click undefined. Okay, whew. Was wondering if we had to write it. Therefore, it can be stated that the function f of x is not continuous at x equals -1 because they didn't equal each other, right? Because we do have a limit, but it does not equal the value of the function. All right, so let's hope for the green arrow or the green check mark. There's a lot of things to fill in, right? Woo! Got our green check mark. All right, so that's how we're going to do these on Delta Math. I'm sorry, I apologize for all the boxes to fill in, but basically that's the way they get us to understand the limit way of talking about, or the calculus way of talking about continuity at a point. All right, so I think we're going to pause here, do a mini practice, make sure you can do these, and then come back if you're at home to the video. All right, so now we've got a different graph, and it says we've got a graph, say all the values of x in the open interval. So this is another way to say what we've got, oops, so sorry, let me switch over here. So we've got -9 to 9, right? Let me pull this down a little bit because I don't think there we go. All right, so, and let's pull that down. All right, so let's look, we're at -9. Okay, can I just remember I don't have my pen? There we go. So we're at -9 to 9, and they're like, okay, what's going on? Which we have a removable discontinuity. So we have to stop and be like, wait, what? What do you mean removable? Let's go back to our first problem. Ooh, I'm going to get rid of all this writing. All right, if we go back to our first problem, there's a lot of places that it's not continuous. And if it's not continuous, we say it has a discontinuity because it's discontinuous, right? And so let's first look at when x is equal to -4. All right, we know because the limit does not equal, we even did this already, the limit does not equal the actual f of -4, that it's not continuous. So we have a discontinuity here, okay? So we're saying discontinuity at x equals -4. Now there's different kinds of discontinuities. There are removable and there are non-removable, right? Anytime a hole is involved, I like to think about the road thing because it's kind of like, oh, that's just a pothole. Let's just fill that in. We can remove that discontinuity. I mean, it might be a big pothole, but we'll just fill that in. So this is a removable one. When we see that we've got just a hole, it doesn't matter if we have a boulder on the top, it's still removable. All right. If let's say we were going along and there was a hole and there's no boulder, it doesn't matter. It's still removable. Okay, so that's a removable one. All right, so let's look at a different one. Let's get rid of what we've written. Let's look at this jump one at -6, right? Remember how we were driving and we had to come to a complete stop because there's a big gap in the road. We can't fix these. I mean, we can, but it's just going to take millions of dollars and lots of manpower. So we would call this a non-removable, right? Same thing. So it's a discontinuity. It'd be a non-removable discontinuity. Same thing when we were driving and we were heading down to nowhere and we couldn't, we're like, when we have infinity, when we're heading off to infinity or we're heading off to negative infinity like here, that is also, once again, really hard to fix that road. Okay, millions and millions, billions of dollars, and no funding. All right, so we're going to say that is also non-removable. Right, it's a discontinuity. If it's not continuous, at that point we say it's a discontinuity, and then we say it's removable or non-removable. Now, delta math goes a little further, and they give you three options. They say it's removable, or say it's an infinite discontinuity or a jump discontinuity. These two, the infinite and the jump, we call those non-removable. So it just depends, who you're asking, but everybody understands those words. All right, so where are they removable? So the removable ones are wherever we see a hole. We see a discontinuity here at -3, right? So we know, oh no, that is non-removable, and we're looking for the removable ones. We're driving along, and it's like, the road ended, and we have to, get, hoisted up to join. So that's non-removable. But at x is equal to 6, we're driving along, and there's just a hole in the road. Okay, we can fill that in. That's removable. So we'll say it's removable at x equals 6. All right, so you'll have fun with those. Let's see what else we have. All right, so do practice those different types of things. Of a few in the mini practice, and then come back. This is not in the notes, but I wanted to talk about it. We know rational functions, and if we were given this rational function, first thing we'd want to do is factor out that x in the numerator, right? So we'd have 4x plus 1, and then factor out the x in the denominator. So we have 2x plus 1, right? And so we would see that our x's cancel out. And we already know when our x's cancel out, we got a hole. So our x's, when x is equal to 0, we should see a hole in the graph. If we're a little guy walking around and here's x is 0, yep, there's our hole right there. All right. But if we remember our rationals, we'd set the rest of the remainder equal to 0, and we would see that we have a vertical asymptote at -1/2. And there it is, right here. This is our vertical asymptote at -1/2. And so when we think about that, it makes sense, right? So cool. That's why the hole, when we have a hole, we say it's a removable discontinuity. Because look, we removed it. We removed it. Isn't that cool? Canceled out and removed it. We cannot remove this vertical asymptote. There's no removing it. All right? Cool, cool. All right, let's go back here. Determine whether the function is continuous at x equals 2. So we're back to piecewise. We love piecewise functions in calculus because they just allow us to really think things through. And so once again, we looked at these. We found the limit, but we never found the continuity. So we have to do two things. First, we have to say to ourselves, are both pieces of the piecewise function continuous functions? Are they everywhere continuous, like no matter what point you pick? And we're going to say yes, because this one is a quadratic. All quadratics are continuous everywhere. And this one is linear, and all linears are continuous everywhere. All right, so that's the first thing. We have to make sure that both pieces are continuous. And then we have to go, okay, so there are two continuous functions that are meeting up at x equals 2. What we have to make sure is where they meet up is the same. So I'm not going to really be drawing these graphs because I'm not going to take the time. But let's pretend like this is our quadratic, and I'm right about here, and then this is our linear, and I'm here. Like, uh-oh, they didn't meet up at 2. We got this huge gap, and we would say it's not continuous, right? But I'm not going to waste my time graphing. I don't need to do that. So instead, what I'm going to do is I'm going to plug in 2 and see what I get. So when I plug in 2, I get what? 4 plus 2 times 4 is 8, so I get 12. Right? Let's plug in 2 here and see what we get. 18 minus 6 is 12. Guess what? They meet up in the same place. They're both continuous, so basically, now once again, this isn't really the graph. So let's see that my quadratic was coming in, and bam, it stopped at 2. I want you to notice my quadratic is the equal, so that would have that closed circle. And then this is my linear, which also at 2 is 12. Now, my linear would have an open circle, but it doesn't matter. There's already a closed circle there. So bam, look at that. Continuity at 2. So what are we doing to find continuity in piecewise functions? We are doing two things. First thing, is it continuous? Yep. Is it continuous? Yep. Quadratics are continuous, linears are continuous. Now, where they meet up, when they're meeting up at -5, do they meet up at the same place as far as the y value? So let's plug in and see if that's true. When I plug in the -5, I get what? 1 minus 25, so I get a -24. When I plug in the -5, I get -12 minus 10, so that's -12. Oh, so close, so close. So at -5, one of them was at, -22, the other was at -24, right? They did not meet up, and once again, I don't know. They're just not meeting up here. All right, so we would say not continuous there. All right, let's see what else we've got. All right, do your mini practice, and then woo-woo, we're done. All right, have fun practicing your Delta Math, and I will see you in class.